Thank you for doing this interview with me. Just to reiterate, my name is Annie, and I created Sustainability Beyond the Lab to highlight sustainable research of today as well as the barriers that prevent its scale up. So, could I ask you to please give a little introduction of yourself as well as your research, especially at Caltech?
I'm Rick Flagan. I am a professor of chemical engineering and of environmental science and engineering at Caltech. And I do research broadly on aerosols, particles, and gases, particularly as related to air quality and climate.
For audiences maybe without a technical background in aerosols, could you kind of explain more about that and what kind of problems do you seek to address with your research?
Well, an aerosol is a system that contains particles in a gas. And it's not a spray can. Spray can generates a very coarse aerosol typically. But aerosols are always around us. In the air, regardless of where you are, there are particles in that air. Most of them are too small for you to see. There are times when they can actually be quite abundant and become quite visible. The infamous Los Angeles smog
Mhm.
is an example of that. The London fogs that plagued London from as early as the 13th century and probably long before that uh, were a very extreme example. They are similar in that they're both man-made anthropogenic sources.
Mhm.
Um, Anthropogenic just being from human beings. Um, and they're the result of emissions of both particles and gases that can condense or can undergo reactions in the atmosphere to form particles. They're the concerns over pollution have been around as long as people have had fire, certainly.
Mhm.
We've all experienced smoke from fires, large scale fires, but if you go camping, you burn a fire, you get the smoke in your eyes. It's uncomfortable. It's also causes a variety of health consequences.
Mhm.
And air pollution is a very broad issue that has been with us for centuries, that got compounded by industrialization. So the earliest well-documented pollution is really the London fogs that received attention with laws as early as Edward II's reign in England
Mhm.
back in 1285 was the first law that I'm aware of. The Los Angeles smog is different from the London smog. The London smog was caused by burning of coal, which released a lot of residual particles from the coal, soot and ash, and sulfur gases that produce sulfuric acid and contributed to that smog and made it quite acidic and noxious.
Mhm.
The word smog was coined back about 1906 by a French physician who was trying to explain that extreme pollution. And he combined the terms smoke and fog, which accurately described what happened in London.
Mhm.
The smog that occurred in the Los Angeles area came about in the mid 40s, although the earliest explorers of the west coast of North America, uh, one by the name of Cabrillo, called San Pedro Bay, the uh, Bay of the Smokes,
Hmm.
and that was I forget the year, somewhere around 1500.
Mm.
So it's been around with us a long time. It's different.
Yeah.
It's more from emitting gases to the air that react under photochemical action. So sunlight can trigger reactions of molecules
Hmm.
that start a chain of reactions that ultimately lead to highly oxidized organics and other species that condense to form particles.
Yeah.
And that's been a big part of what I've been working on. It was extremely severe when I first moved to Southern California.
Hmm.
Um, but it started even before I was born. There was a very major episode when a butadiene plant, a plant making a precursor for synthetic rubber,
Hmm.
started up in 1943 in Los Angeles. And when it started up, it immediately started generating an intense brown haze. And in fact, was shut down the day after it started
Hmm.
until they could clean up their act quite a bit. And even that did not work. It took quite a few years before people understood that it was what was emitted by cars
Hmm.
that was under contributing with the organics released by that and other processes in the area that were producing the infamous brown haze
Hmm.
that fortunately we don't see anymore.
Yeah.
So my work started out focused on that smog, the Los Angeles smog, and trying
Hmm.
to understand it and trying to help provide the information that would guide the agencies charged with cleaning up the air with the tools they needed to do it.
Hmm.
And many people were involved in that. The guy who really got it started was a professor here at Caltech. He was studying, he was a biochemist, and he uncovered the fundamental mechanism behind the photochemical smog
Hmm.
as he was trying to figure out what was killing the plants that he was studying. So I've been involved in that. Gradually, the work evolved to expand beyond the local regions to address issues of climate change. And
Hmm.
in climate change, the particles in the air are the biggest source of uncertainty in our ability to predict what is happening to climate.
Mm.
That they scatter, the particles reflect a lot of sunlight back to space.
Yeah.
And so they provide cooling while the greenhouse gases are leading to
Hmm.
warming. And
Yeah.
it's the combination of the two
Hmm.
that
Are, oh, sorry to cut you off.
yeah, go ahead.
Yeah. Just to clarify, are aerosols generally considered beneficial, like for reflecting the sunlight back into space? Or are
No,
they?
no, there are people who are trying to propose that.
Mhm.
Particularly, there there is a there are proposals for marine cloud brightening
Mhm.
to take the low-level clouds that you see when you fly over the oceans and make them brighter so they reflect more sunlight back to space to cool the Earth. Those efforts are relatively short-lived,
Mhm.
which means they're reversible.
Mhm. Oh, I see.
And as such, experiments done with them, if they're not releasing things that are toxic or have other long-term effects, you know, dumping chemicals onto land or into the ocean that could have detrimental effects. Without that, those are relatively benign. There also are the people who are proposing that we should inject particles into the stratosphere,
Mhm.
particles or gases that would make particles and produce clouds that would reflect more sunlight in the high atmosphere. Now, those will have a lifetime of a few years, and as such, they're potentially much more damaging because we don't really know quantitatively how they will behave.
Hmm.
Um, it's a rather extreme bit of hubris to say that we can conduct this big experiment intentionally modifying the atmosphere in order to solve a problem that we've
Yeah.
created.
Yeah, definitely.
That one makes me very nervous.
Hmm. Um, your research spans like from like atmospheric science to these aerosols. Are there any like specific projects that you think are really interesting or exciting within this field?
Well, a lot of what I've done over the years has been trying to get the data that we
Hmm.
need to understand what's going on.
Yeah.
And there is a project that I'm involved in that a former student has led, that's Sally Ing, who has recently joined the faculty at Caltech. And this is a project that set up a network of a small number, a dozen stations around the country,
Hmm.
from urban areas like Los Angeles, Riverside, going out to the desert in Joshua Tree, up into Alaska, in extreme, you know, background locations, but spread all over the country. It's a very low density of samplers, but what they do is they provide real-time data.
Hmm.
And that real-time data we will soon have available to the whole world to see in real time
Yeah.
as it's collected. And that's proving to be very important.
Hmm.
We had in Los Angeles in January of 2025, we had two major fires develop in the Los Angeles area.
Yeah.
One was the Palisades fire on the northwest side of Los Angeles in the mountains and blowing smoke out over the ocean. It was an intense fire, burned a lot of homes, killed a number of people. Um, that was one. And that one was in an area where there was limited data being gathered.
Hmm.
There's a second fire that occurred in Altadena, the Eaton fire, and that one was upwind of one of the net stations of this ascent network, which caught the smoke.
Hmm.
And so as that fire burned, we started seeing high concentrations of lead in the atmospheric aerosol because we had this real-time chemical data.
Yeah.
And that became a high priority to get that information out there. The
Yeah.
people who were affected needed to know what it was they were breathing. They needed to
Yeah.
know there are
Definitely.
serious health consequences.
Hmm.
Um, and so this move from what the Environmental Protection Agency mandated decades ago for monitoring and controlling and trying to control air quality, but doing sampling that was very expensive. They would typically collect samples one day out of three or one day out of six, trying to rotate it so you wouldn't catch the same days of the week every single week,
Hmm.
catch weekend versus weekday effects, for example. Um, and going to getting that information in real time.
Yeah.
It's been very informative. It's not nearly enough. And so one of the main things that my research is doing right now is looking at how we can take the instruments
Hmm.
and transform them into ones that we can afford to put with the density we need to monitor air quality so that we can really map what people are being exposed to.
Yeah.
And more importantly, map what is the dose of pollutants that people are inhaling so that we can start trying to do a better job of linking those air quality impacts to human health.
Hmm. Yeah, it's really interesting hearing how like important the data is, or how important quantitative data is in your research as well as the work that you're currently doing. Um, Focusing more on kind of the scaling up aspect, what kind of barriers do you think are most prominent in preventing the scale up of these sustainable technologies, including your very promising research? Do you think it's more like policy related or economic, or maybe even about the scientific innovation itself?
It's a combination of things.
Yeah.
One is there's a big political component.
Hmm.
We have had a clear need to control air quality for decades and
Yeah.
going back to London for centuries. And it's not just London, it was throughout China as well. You can find it in the right, find out discussion of air pollution in the writings of Plato and
Hmm.
you know, other early scholars. But there are also people who are trying to develop a business. And suddenly people come in and say, you can't run your business the way you want to. You have to take into account these things that you don't even see or notice when you emit them out your smokestacks
Hmm.
or your tailpipe of your car. That we have to control things that are accidents of how the technology developed. They're byproducts, really small concentrations sometimes,
Hmm.
but they have huge effects. So there's a big political issue. We
Hmm.
have the people who look at the health, the air quality, the comfort, the visibility. Can we see the mountains? For here they're 5 miles away. When I first came here, you could be here for months and not know there were mountains anywhere nearby.
Yeah.
There are very different vantage points on this. So that's one factor.
Yeah.
And we just had a bunch of people who violated the Clean Air Act,
Hmm.
pardoned for their crimes because they were so trivial in the eyes of a political leader.
Hmm.
That, in my view, is inexcusable.
Yeah, definitely.
The so we have these different factors, but there are other issues as well. One is cost.
Hmm.
The stations that we set up, these dozen stations, each of them costs about $1 million with all the equipment. We
Hmm.
can't afford to put one of those at every air quality monitoring station in the country.
Hmm.
There are 10 to 15,000 stations that are supporting the EPA mandates. That would be an awful lot of money to spend
Yeah.
to support the air quality. So we have to find better ways to do that. There are lower cost sensors. There is a big push now for using low cost sensors for measuring particles. There are some that were originally designed to tell building operators when it was time to change their filters on their ventilation system in China.
Hmm.
They could, by telling the people who wanted to rent that they were monitoring the air quality and they were making sure their system was working well, they could get higher rent. So
Hmm.
it's an economic incentive. And
Yeah.
these are little $2 sensors. unfortunately, they're not quantitative, they're not reproducible. If you go out and you buy a purple air, you're buying a couple of these few dollar sensors, a lot more with tariffs and so on. But
Hmm.
the ones that I bought years ago to see how they worked uh, were I think I probably paid $10 or $15 for them. So quite expensive to compared to what they
Yeah.
cost to make. But they don't provide the data that we really need. We have instruments that can provide that data, but they are made in small numbers. And being made in small numbers, they are very, very expensive.
Hmm.
So a standard instrument that would let you measure the size distribution of the particles in the air costs about $100,000. Again, if you put that over 10,000 stations, it adds up.
Yeah.
The the instruments are not that complicated.
Hmm.
The techniques have been around for a long time. This measurement for getting the size distributions, the first version of that instrument that I've been able to find in the literature was published in a physics journal in 1918.
Wow.
Oh, oh, well over a century ago.
Yeah.
It's been around for a long time. They became commercially available in 1975. They became practical for making rapid measurements with about 1990,
Hmm.
with a combination of additional developments and some creativity. Measurements were made much more practical, but they're not that complicated. But they're produced by companies that are selling a few instruments, and they have to put all of their costs onto a few relatively smaller number of instruments.
Hmm.
So we need to rethink how we make the measurements, how we produce the measurements. If we were making measurements at all 10,000 stations in the country, those companies could make a decent profit on a much lower price.
Yeah.
They'd love to sell them at the price they're doing now
Hmm.
and say, that's the real value. But they've been selling them at that price or at prices that were lower dollars, but are same magnitude of real cost for
Hmm.
half a century. So we have to rethink how we make the measurements.
Yeah.
I think it's possible to do a lot, but it requires a commitment and it requires a totally different
Yeah.
business model. It's
Definitely.
not going to happen with the companies that are doing it now in the mode of business that they're doing it now.
Hmm. It's really interesting to hear your perspective on that. Especially like kind of the history of like air quality or atmospheric science as well. Um, Throughout your career, what do you think has been like the most interesting or exciting evolvements of atmospheric science or aerosols?
It's it's been taking the how to say this, the chemistry that goes on in the atmosphere. We have very complex chemistry. If you emit one hydrocarbon into the atmosphere and watch how that will react, pretty soon you will have thousands of different molecules present.
Hmm.
And it's been a very slow process in trying to unravel that chemistry. It required designing experiments that gave you control. If you go outside and monitor what's in the air, what you're measuring at any instant of time is the effect of everything upwind from you.
Hmm.
that has added chemicals to it, all the reactions that have taken place, the winds, the mixing throughout the atmosphere, all of this complexity comes in. We couldn't at the time, certainly, uh, unravel those details.
Hmm.
What we had to do was to find ways to do a controlled experiment. And to do that, we built some chambers. I wasn't the first person to build them. I found a way to help make them clean enough that we could start unraveling the chemistry,
Hmm.
at the same time having the reactors large enough to be able to study the particles, which
Hmm.
the particles will be lost to the walls. So if you release particles to the wall, to your room where you are now, very
Yeah.
quickly the concentration will fall as those particles diffuse to and deposit on the walls.
Mm.
The chambers that we used initially were ordered 60 cubic meters in volume, 60 cubic yards. So it's a pretty big size. That's the mass of air is about 60 kilograms.
Hmm.
So well over 100 pounds of air.
Yeah.
And most people don't think about air as in terms of its
Yeah.
mass. It's massive. And the amounts of particles that are in there, they're micrograms per cubic meter. And some of the chemical species we're looking at are at 1 part in a million or 1 part in a billion or even lower concentrations, but they still are important. By doing controlled experiments, we could know what chemicals we started with and follow that evolution.
Mm. Yeah. Definitely.
Initially, the measurements we made were rather limited and indirect. We could measure how much particulate matter was being produced. We weren't getting the detailed chemistry. Even when we got the chemistry, it was just indicators of some of the basic elements of the chemical structures, but not molecule by molecule.
Mhm.
Today it's different. Not that we can do it routinely, but there exist mass spectrometers where we can see those thousands of molecules.
Mhm.
We can't get the chemical structure of every molecule, but what we can see is with gentle ionization and mass spectrometry, we can measure the masses of the individual molecules. And so we will see thousands of peaks in the mass, in the distribution of
Yeah.
masses in the gas phase that we're looking at. And then we can look at the particles with similar kinds of capabilities.
Mhm.
So, it's been a gradual evolution driven by a combination of measurements and theory. So the theory would advance up to the point they could explain all the measurements.
Mhm.
But then trying to go beyond that, you have no way to test whether what you're looking at is of any use until the data gets better. So it's
Yeah.
been sort of a leapfrog with the
Yeah.
experiments in improving and then the theory and
Mhm.
so on. And
Yeah.
that's been going on for decades.
It's really interesting to hear a perspective from like the evolution over the course of many years. Before we wrap up, is there anything that we didn't get to discuss that you think is really important for general audiences to know about sustainable research or atmospheric science, or anything you want to tell to next generation researchers?
Well, you don't know where your research is going to go.
Mhm.
I started out when I did my graduate work, I studied combustion, I studied uh, formation of nitrogen oxides from the organically bound nitrogen in fossil fuels. I came to Los Angeles and I was immersed in the smog and developed a collaboration with John Seinfeld, a colleague here, And he was a theorist, and I focused on the experiments, and we made a good team. And over half a century, helped to unravel a lot of what's going on and help to empower other people to go beyond. So John developed the first large-scale air quality models. I advanced the measurements. The two were integrated together at every step along the way. You don't know where your work's going to go.
Yeah.
Sometimes the most frustrating puzzles that you face, the ones that you can't seem to resolve, turn out to be the most important and interesting.
Hmm.
So we've had breakthroughs, one evening preparing a lecture for a class that it was a topic that I really didn't enjoy because I was talking about an instrument that
Hmm.
I thought had left a lot to be desired. I looked at it a different way, and the next day gave my class a lecture about an instrument that didn't exist. And then 2 weeks later, we had them using it in the laboratory because what it took was just taking a tool that we had and changing how we use it. You never know what's going to click and when. There have been ideas questions I've been trying to solve for decades. And after many failed attempts, you finally find that connection that actually works.
Hmm.
And so the frustration is often the source of creativity. It really pushes you to try to find ways to solve problems that you don't have a clue how to solve.
Hmm. But yeah,
And
thank you. That was really interesting to hear your research on like atmospheric science as well as your perspective on like attitude towards research as well as kind of the history of aerosols and atmospheric science. But yeah, thank you for taking time to do this interview with me.
okay, you're so welcome. And I hope it's of use to people.